this, which is when you get a question and it's about invertibility and you don't know anything about the inverses existing, what are you going to work with? What's your tool? Basically, immediately, you're going to work with injectivity, right? You always have like ST invertible implies ST injective. What does it mean to be injective? I want at least 3 different things that means. Okay, the null space, so that's the same as saying that the null space of ST is just the 0 vector. What else does it mean? Perfect. Anything else? Dimension of the null space of ST is equal to the 0. That's good. Okay, another one. So the null space is 0. Applications, the same outputs implies the same inputs. The dimension of the null space is nothing. I would think of one that frequently comes up that's just directly related to this that we use all the time when we're doing injectivity arguments. What's that? Okay, that's true if it's finite dimensional. There's a theorem that says that. So yeah, you could, if you have finite dimensional vector space, you can also hook this into, invertible, injective, surjective, and bijective.
Not always use surjective because aren't all.
If your vector space is.
Are they always in this class?
No. If it's not stated that a vector space is finite dimensional, you can't assume it. You get to assume what's there on the page. Okay. And that's why you should think of injectivity as being the thing that matters here, right? Injectivity is a test for this. In fact, it's not, yeah, you should be careful with this, right? Like I will not set up I'm not going to trick you guys, just be careful, okay? What's the most common way that this gets used in a proof? Null space of ST being equal to 0. How does that actually show up in practice? That's a cool thing to say. Oh, the null space is just the 0 vector, but how does it show up in practice? Okay, that's more related to this guy, but yes. Okay, so the fundamental theorem of linear maps says that the dimension of V is equal to the dimension of the null space of ST plus the dimension of the range of ST, and that term isn't there. You have it. It's that, that line shows up all the time in arguments, right? When you're working with a map that's invertible or injectivity, very frequently you end up looking at an equation that looks like this. What can you say about V in that equation? Not equal to 0? It must be equal to 0, right? V, if ST is injective and ST sends V to 0, it well better be the case. V is equal to 0, right? We use this constantly in the exercises, in the homework here, right? And so what I'm trying to say with this discussion is this gives you a range of approaches that you can take to a question. And so when you see something with invertibility and you haven't been told, you're testing for invertibility. These are the typical ways that you do it. And I would say the single most common way that this gets done is this. Using the idea that this thing being equal to 0 forces V to be equal to 0. That showed up a lot in the homework exercises when ST is injective. Okay, so none of these is the definition of what it means to be invertible necessarily, but all of them turn out to be equivalent to injectivity. Invertible implies injective. Injective is equivalent to all of these things. This gives you a big range of tools you can work with in an exercise. How does that show up in this argument? ST is invertible. Show that S and T are invertible. Let's suppose here that V is finite dimensional. For the sake of argument, what am I going to do? Yep. Okay. So. Okay, so let's suppose that ST is invertible. which implies that ST is injective. Yep.
It's a lot like with groups that you kind of like people say one or the other. Never
Well, he's Axler. You think about Axler as the guy on top of the mountain giving wisdom, right? And you're at the bottom of the mountain trying to convince me that you understand why that's true. Yes, you have to be. I mean, on an exam, it's not going to hurt you on an exam to be more detailed than you would be necessarily. Like, I mean, you should live in. I'm not going to say fear, but you should think if your professor could reasonably point to a line and say, why is that true? And you could immediately say it in one sentence. Oh, it's because invertible and injective are the same thing. Was it worth taking the time to write it down on the paper? And the answer is probably going to be yes. Right? It doesn't even have to be like a whole argument. It could just be like it's injective because it's invertible, right? Because ST is invertible, it's also injective. Okay. So let's suppose you were faced with a question like this in an exam. What's your move from here? Somebody pointed out, like, what's a strategy you might take? Got to do something. There you are. You're sitting on a test. Your friendly neighborhood math professor gave you this question, and you're just sitting there eyeballing it. Like you did the other direction by like really quickly, or maybe he was even nicer and just wrote it down in one direction and said, "Prove this. Prove that if ST is invertible, then each of the pieces must have been." So you want to say STB equals 0. So that right there, all you've told me is that V is equal to the 0 vector, right? Oh, so you want to start with this and say that this is equal to STV.
And then say EV equals 0, which implies that E is projected. And then S times 0, get that 0
By 3.1, what? Yeah, it's like the media over here. What's that? Yeah. I'm just impressed that you actually have the number in your head. Okay, so what you're saying is that if this turned out to be equal to, so if this was equal to 0, it would all that means like what are you trying to say here?
I mean, I could.
I'm just curious. I want to make sure I follow your argument. This is a good approach to this. This is typical of the approaches to these questions.
Go piece by piece with parentheses showing that.
So if S was injective, if S was injective, you don't know S is injective, but if it was, then that would force TV to be 0, right? But you don't know S is injective. This is a good exploration of the approach to the question.
Do we need to know that S and T are linear maps? Like
Oh, I mean, you could just assume everywhere ST and S and T are all in. Yeah, that's going to be a hard part of the hypothesis of the question. Yep.
For this one, you have to know that S is injective, or can we say because S is linear, it maps?
Oh no, you need more than linear. The fact that it's linear, I mean, if TV was equal to 0, then S of TV would be equal to 0. By what you're saying, right? If TV was equal to 0, then S of 0 would be equal to 0. Yep. What's that? Yeah. Give me ideas.
Be sure that TV is equal to TU and apply this to both sides.
Okay, so your approach is to say, let U and V be and B. So you're trying to so you're going to establish that T is injective. Okay. So the idea of your argument is you're going to assume this, and then somewhere down the line you're going to show that U is equal to V. Remember, this is one of the sort of pieces that we're trying to work with, right? So okay, what's your idea here? That's perfect. That establishes injectivity of T. Okay, so now T is injective. But now that lets you use the first part of the argument, which lets you conclude that S is injective, right? So now you know that T is injective, which means if T of E is equal to 0, if V was equal to 0, then if this vector is equal to 0, then this vector must be equal to 0, right? So however you approach it, the idea here in this question is, notice nowhere did we use the symbol S inverse or T inverse, right? This is a sort of a bootstrap argument. I actually did it slightly differently when I did it, but in both cases, the idea is establish that that the inside operator has some property, and then once you have that, you get that forever. Notice we didn't use anything else about other than ST is injective to get this. So this is, you can think about this as, you know, if you were really feeling fancy, you could call it a lemma, right? That I proved some partial result that I need for the rest of the proof, right? From this point forward, you now get to assume that T is injective. Okay. But the approach to this was to try to use something about the definition of injectivity. Yep.
Are S and T defined as like operators?
Yeah.
So then when you say it's injective, that it goes, then it's obviously.
Yeah. So
Okay.
because we're operators on a finite dimensional vector space, this would be the sort of thing that would be useful to put at the top of a proof that gets asked is, hey, it's finite dimensional, so injective is equivalent to invertible. And for the rest of the proof, I'm going to use injective and invertible interchangeably, right? Just note somewhere that you understand that that theorem is at play. Yep. It's possible to have an injective operator that is not invertible, and it's possible to have so injective operators that are not invertible in infinite dimensional vector spaces. So you imagine that you have an infinite dimensional vector space that looks like V1, V2 forever, right? There's a basis. So it's the span of an infinite collection of vectors. Now, I'm going to define an operator like this. T of Vk is equal to V2k. That's injective. Every input goes to a unique output, right? Because but I'm missing a bunch of the basis. So it's an injective operator, but it's not surjective. And likewise, it's possible to construct a surjective operator that's not injective. Yes, badly. Which?
Why it fails.
Okay, so what I'm doing is like this. I want you to imagine I've got a vector up here, V, which is equal to C1, V1 plus C2, V2 out to forever, right? Some infinite like vector that's in this infinite span, whatever that means. And then let TV take this and turn it into C1, V2, C2, V4, C3, V6, where I just I send the first basis vector to the second, and the second to the fourth, and the third to the sixth, and the fourth to the eighth. That's a well-defined map. This is injective because I can tell you exactly where this lands and get back to where it came from, right? This is a one-to-one map. Everything here has a unique thing that it came from. So this map is injective. T is injective. Is T invertible? And the answer is, well, can I undo this map? Where does, if I apply anything in the range here, in the span of these vectors, where does V1 go back to? Right? Do I land on V1 anywhere? Can I ever get V1 out of this map? And the answer is no, I skipped it. Can I get V3 out of the map? No. So this is an injective map that has an infinite dimensional range that fails to hit an infinite dimensional space of like subspace. So what the linear map, I mean, I guess the fundamental theorem of linear maps would say infinity is equal to infinity plus infinity minus infinity, minus 0. That's not a very interesting thing to say, right? The range of this map is infinite dimensional. The null space of the map is actually it's 0 or something like that. But like you can't do this. You don't have the way that infinities interact with each other is not the way that you suspect they should. Right? That you can't really use the fundamental theorem of linear maps to classify things because you can have things flopping around to infinity.
So for this, when you let T equal TV and then you apply S.
Yes.
And then the ultimate like solution is U equals V.
Yeah, so if TU is equal to TV, then STU is equal to STV, which implies that U equals V.
Can you say that S of T is injective?
No, not yet. Because what we assumed here was this. We assumed this is our condition and we derived that U equals V. The next step would be to say, okay, now assume S, if you want to, you can say now assume STU is equal to STV. This is a different hypothesis. Here that this is the hypothesis, right? And then I applied S and I derived this. Now, oh yeah, the problem here is like, what do I do with S? But that doesn't tell me, okay, so S applied to, doesn't help. What would I actually need to, so the goal was not to show that ST, we already know ST is injective. If I know T is injective now, what's the next goal of this argument? I got to show S is injective. What's a good way to do that? Where S is invertible. I've got two possible approaches to showing that S is invertible. I can show that S is, since we're in a finite dimensional vector space, I could show that S is surjective, or I could show S is injective. In either case, I'm going to get the result that I want, right? What would I need to say in order to say that S is injective? What would need to be true? What's the hypothesis for S being injective? SU, so assume that U and V are in V so that SU is equal to SV. Damn, now what? Oh, T is injective, so therefore T is surjective. In a finite dimensional vector space, those are equivalent to each other. How can I get a T into the picture here using surjectivity? U must be equal to T of some vector, right? This is in the range of T, and this is also in the range of T. So because T is surjective, U is equal to T of W, V is equal to T of Z, I guess, for some W and Z and V, right? That's what it means to be surjective. Everything is in the range. Well, that means that SU is equal to SV implies that STW is equal to STZ. What can you say about W and Z? They must have been the same, right? Why? ST is injective, so W and Z are the same. But if W and Z are the same, what do you know about U and V? This implies that W is equal to Z because ST is injective. But if W is equal to Z, that means that U and V must be the same vector. So we started with SU is equal to SV, and we showed that U is equal to V, which implies S is injective. Now this problem is more complicated than I would ask you on an exam because there's like a two-stage approach to this, but it's not that bad. And you should expect that you're going to be asked to show something simple, like a partial version of this question might say, suppose ST is invertible, prove that T is. It's half the argument, but the basic idea is still there, right? Yep.
So how do you go from T is injective to?
From T is surjective. Well, what does it mean to be surjective? Definition check. What does it mean that, okay, so we did this already with injectivity. Let's do it with surjectivity. Okay, so T is surjective. First off, what's the definition of surjective? Range T is, well, in this, let's assume that T is an operator. The range T of it is V. Okay, boom, you did it. You wrote down the definition of what it means for an operator to be surjective. Now, equivalent characterizations. Every, what's somebody say? Not quite. It's that every vector in V is an output. Every vector in V is an output of T.
That's not the same as every output.
No. Because when you say output, I think about element of the range. When you say output, I think range, right? You need codomain here, right? Every vector in V, every V in V has V equals TW for some W.
Yeah, I guess every output has an input is kind of just like
I mean, what you're saying is this line, right? I mean, I think this is the idea that you're after.
Yeah,
here. But yeah, the subtlety here is you can always do this for any vector. If T is surjective, you can always write any vector in the space as T times some other vector. And that's what we did right here. T is surjective, which means any vector in the space can be written as T times some other vector. Common move in these exercises to have to do that, right? This is this thing right here. How does this show up in arguments most commonly? You say, oh, well, I got some V and V. Oh, but T is surjective. So V is equal to TW. That's the most common way that surjectivity gets used in the arguments, is to like somehow produce the vector T or the operator T from some like random vector V. I mean, what we needed here was to somehow get a T into this equation, and we used surjectivity to do it. This is a good exercise because there's a lot of these pieces. I mean, yeah, T is an operator. Right? If T is an operator, then yeah, I mean, it just comes from the fact that T is a, you wouldn't even call it a function if that wasn't true. What else? Yep.
I have a question, just like a conceptual question. I know how like T minus lambda I comes from an eigenvalue equation, but what's the importance of saying that that's not objective?
Okay.
What is that?
So that's a really important point here. So let's talk about that. Okay, I want you guys in your heads, or maybe somebody brave can raise their hand and tell me what's the definition of what it means for T to have an eigenvalue. Definition.
A number, lambda, and
Okay, so lambda, say lambda is an eigenvalue of T.
F. If the just a V.
Nope. Nope. No. I don't think that is a derivation, right? That's not actually the way that it's set up. That's a second order property that eigenvalues have that you're talking about. But if I remember correctly, I'm gonna look at this real quick just to make sure I'm not telling you no when you're actually right here. But I believe that eigenvalues are set up in terms of kernels of operators.
Does that have to do with TV is equal to lambda?
Oh no, you're right. Never mind. Yeah, so Axler does it the other way. So you are correct. Okay, so go ahead and continue. If there exists a V and V with V not equal to 0, V is equal to lambda V. Okay, so yes, completely correct. I stand corrected. Now, the property that I consider to be the definition in some texts is the other direction, which is, or the other version of this involves null spaces. This is the version that you're talking about, right? So what would it mean for this equation to be true? Go ahead. That we'll get, you're almost right.
Lambda is an eigenvalue of minus lambda I is not.
Okay. That's what I sort of like. I like the way that we often use it is like, I just came out of a class where we use that as a definition, which is why I told you we're wrong. So I apologize. Okay, so but the question of how this relates to this null space thing is, what would it mean for this equation to be true for some non-zero vector? This is a move you should be able to do because it shows up all the time. This is why it's worth taking the time to actually look at this. It means that TV minus lambda V is a 0 vector. And that means that T minus lambda I V is equal to 0, where V is not the 0 vector. Yeah. It does mean that V is in the null space. It means that the null space of T minus lambda I contains V, which is not the 0 vector. Hence injectivity, right? So this is actually, I guess this is, the way Axler sets this up is he derives this as a property. This is the definition, he derives this as a property, right? And then you say, that means that T minus lambda I is not injective because the null space isn't just the 0 vector.
similar way for surjective.
Yeah, so they're just equivalent. So that we have that equivalence theorem that says in the finite dimensional vector space, invertible and injective and surjective are the same thing. That means not injective, not invertible, and not surjective are also all equivalent. Okay. So that means that I can ask you questions like, here's one. This came up as part of a homework question, and I want you guys to be able to like think about how you would do this. Suppose t to the n was equal to 0 for some n. So t to the n here means repeatedly apply t to itself, and eventually you get the 0 operator out the other side. Okay. Show that lambda equals 0 is the only eigenvalue. Of t. There you go. That's an exam-like question, right? Not a homework question because it's cut down to the core of the argument. You've got t to the n is equal to 0 for some power n. Show lambda equals 0 is the only eigenvector for t, or eigenvalue for t. How would you do that? What's step 1? Nothing. T to the n, t is an operator. T is in L of v, and t to the n is equal to 0. That's what you get to assume. Got that? Okay, suppose that lambda is an eigenvalue of t. If you're going to show that the only eigenvalue of t is 0, start with the general eigenvalue and try to show that the only possibility is that lambda is equal to 0, right? Standard sort of move here. Pick an eigenvalue and do algebra that shows that it must be the case that lambda is equal to 0. Now what? Okay. Because Axler says to assume always that V is complex, is over C. So we're always have an eigenvalue, right? So good question though, yeah. So like in the absence of in the absence of saying the real numbers, assume everything is complex, and so operators always have an eigenvalue. So what do you do? Yep.
Introduce an eigenvector V.
Okay. Then there exists a V in V with V not equal to 0, so that TV is equal to lambda V. If you're doing an eigenvalue equation and you manage to avoid writing down the eigenvalue equation, I'm going to be impressed. That better show up somewhere if you're working with eigenvalues. I promise you, you go through a test and that's not on your test somewhere. You should go back and figure out where it was supposed to be. Okay, great. Now what? What have we not used? See, when you're doing a problem like this, one of the hardest things in a question and why we're talking about this, when you're looking at a proof like this, okay, it seems like I've exhausted my definitions at this point, right? I've used definitions. The definitions say, oh, I've got an eigenvalue. Okay, so I know what it means to be an eigenvalue. So I've done all my definitions, but I have this hypothesis lingering up here that I haven't done anything with yet. You know? What do you mean?
Did you raise the t to the n?
Okay, so what would this be? What's t of v? So on the one hand, this is t squared v, and on the other hand, t of v is t of lambda v, which is lambda t of v, which is lambda squared v, right? Okay. So this same idea, if you keep spinning it around, you're going to get that TNV is equal to lambda to the NV. What else do you know about T to the NV? Well, it's the 0 operator, right? So this is equal to 0V, which is? So what can you conclude? Why? Why am I allowed to conclude that? Because V is not 0. this is why we had to make sure that we wrote this down, that we know this is not a zero vector, right? Because once we know this isn't zero, if I have a scalar times a vector is equal to zero, then either one of them is equal to zero or the other one is. This implies that lambda to the n is equal to zero because b is not equal to zero, and that means that lambda is equal to zero. So if you're an eigenvalue, you are a zero. Yep.
So on the exam, are we allowed to assume that n of b is equal to
That is a
zero?
good question. So you are allowed to assume anything that was covered in the book or the homework unless you're asked about it on that particular question. So you can't use a homework exercise to prove the same homework exercise that you're working on. But yeah, that would be the sort of thing that, like, if you were going to use this in practice, if you were going to use the fact that TNV is equal to lambda to the NV, you should at least tell me that, like, that you know that's true.
You gotta show at least how you got.
Yeah, I mean, if in doubt, either raise your hand and ask me the question, like if I want you to show it or not, or just say, look, t squared v is equal to lambda squared v, and you can just keep going to get the same thing for tv. And so, you know, continuing by, you know, say by induction, you say, so tvnv is equal to lambda. Okay.
If t has an eigenvalue, does that mean t is arbitrary?
Okay, that's a good question. So no. So the question was, if t has an eigenvalue, does that mean the matrix of t is upper triangular? And the answer is no. But it means, like, we have a more powerful theorem than that that says that every operator has an eigenvalue. And we use that to show that every operator has there's a basis that we can use to find an upper triangular. Then if you have that basis, then it's upper triangular. Yeah, any operator, for any operator, you can find a basis of that matrix is upper triangular. Okay. What else should we talk about here? Yep.
Number 2 from reading.
Which one was that one? Ha, okay, this is a great one. Why is the set of non-invertible matrices not a subspace? Why not? Okay, so this is perfect. You're right. It's not closed under addition. If you want to prove to me that it's not closed under addition, how would you do that? You just give me an example. So the question is, prove that the set of non-invertible operators is not a subspace. Yep.
Can we do this? Like, if B as like R2 and then
You literally, all you have to do is literally write down one example of a vector space and one example of a subspace of that is not a subspace. So if you want to talk about 2x2 matrices and write me down 2x2 matrices that don't stay in the family of non-invertible 2x2 matrices, you can do that. So does anybody have an example that shows the non-invertible operator? I'm going to write you a non-invertible operator. I write one. There you go. This thing is an operator T, which is a T of V, which is equal to 1000 V. That's not invertible. Why? Because it spits out things that look like this. Pretty badly not surjective, right? Never has a y coordinate. That's not invertible. I'll give you another one. S of V, which equals 0001 V, which is 0y. Also not invertible, right? Neither one of those is injective at all, or is surjective. What if you add them? Get the identity. Is that invertible? About the most invertible, right? Zone inverse. So if you took T and you added it to S of V, then you get T of V plus S of V. Why is that true, by the way? Why is T plus S of V equal to TV plus SV?
Some of them. There's a definition.
I still haven't heard the answer I'm looking for. Because LV is a vector space. And we defined the addition on LV to make this true. This is the addition operation on the vector space of operators is defined so that this is true. I'm not. That is like the nitpickiest of the nitpicks for the question I asked. I don't like to ask nitpicky questions. All right, what the hell were we even talking about? Oh yeah, what's T plus S? Well, T plus S of V is TV plus S of V, which is X0 plus 0Y, which is equal to, oh, it's the identity. T plus S is the identity map. That's invertible. So that means I'm not closed under addition. Because I started with two things that weren't invertible, but I added them into something that was. So I'm not closed, so I'm not a subspace.
I have a question just from like the study guide, and it said, suppose T is in L of V to W and V1 to Vn is a list of vectors in T.
Okay.
And then it says if T of V to T of Vn is the linear
Uh-huh.
independent, V1 to Vn
Uh-huh.
are linearly independent, and
What a beautiful question that is.
I need help on the converse.
Okay. So the
Like, just
idea
the
is, so you have
converse.
T in L of VW. And
And then V1 to Vn is a list of vectors.
is a list in V. And the claim is V1 through Vn linearly independent if and only if TV1 to TVN linearly independent. That can't
Okay,
be
so,
true.
well, it started, if T of V1 through T of Vn is linearly independent, then V1 through Vn.
Huh?
And it said, is the converse true?
Oh,
So I
okay.
need help with that.
Is it?
I can't show that it is linear.
Okay, I'm gonna give you a strategy for the counterexample type things. What is the stupidest operator?
Zero.
The zero operator, right? There's the two stupidest operators that turn out to like oftentimes be things you should test are T is equal to 0 and T is equal to I, right? Now, what happens? What happens? See, what we're trying to prove here is if,
If V1 through Vn, is it true that if V1 through Vn is linearly independent, then?
what do you think? If V1 through Vm is linearly independent, does T of V1 through T of Vm have to be linearly independent? What if T happened to be the zero operator? Then no. And all you have to do to exhibit that something is false is to show one counterexample. And that's why keeping stupid things like this in mind is a good idea. Test it on these dumb cases, right? Because sometimes these things are false with really dumb applications, right? Like, well, who cares what the linear, these could be anything you want. If you send them all to 0, then the output can't be a linearly independent set. Now, a better question would be, what conditions would I need to add to T to make the output linearly independent? I'm actually curious. What would I need to, what do I need to be able to say about T to guarantee that a linearly independent input, that a linearly independent list is carried to a linearly independent list? All right, I got back. I heard from Matt. Yeah. Okay. Anybody else have an idea here? Is that what you're gonna say? Is that what you say? Anybody have any other answers? It is injectivity is the best way to say that, right? Injectivity preserves linear independence. It's guaranteed to preserve. Define a dimensional vector space. Yep. Oh no, that would be a thing I'd ask you to prove. I was going to ask you to prove. It would be like show that if T is injective, then an independent list is carried to an independent list, which would be worth thinking about. Okay, now we're in the panic zone. Yep. Okay. So isomorphism is sort of like invertible, but where the vector spaces are different. We restrict when we talk about invertibility, we talk about invertibility with respect to operators, right? So if I have T in LV, if T is bijective, call T invertible. Right? So a bijective map in the context of operators is invertible. If I have S, sorry, acting from a space V to W, and it's still a map that can be undone. So a bijection between V and W is still a map that you can think of as being invertible in the sense that I know where every point goes to and I know where every point comes from, right? Here, if S is a bijection, we say S is an isomorphism. The idea is exactly the same. So an invertible map is just an isomorphism. An invertible map is an isomorphism of a space onto itself. And an isomorphism is just a bijective map between two different vector spaces. Right? But the idea is the same. All the only difference is this still contains the idea of bijection. Normally, when we think about isomorphism, what we're thinking is V and W are the same vector spaces. Okay. Yeah, the dimension of W and the dimension of V are the same, right? Or if I have some like F plus G over here that I can go back and look at like the image, the pre-image, everything over here is the output of a map. And I could actually go back over here and do the same operation. It's the idea that like T of S plus W is equal to TS plus TW. This is the same thing as saying, oh, well, if I have a U plus V over on this side, I can write U as equal to being TW and TV, or TZ, and then pull the T out to get W plus Z. The fact that I'm a bijection means that it doesn't actually matter where I do the addition, I get the same result. The vector spaces are essentially the same. So Axler is really careful about distinguishing these ideas. It's not the worst thing in the world if you think about these things as invertible, as maps that have inverses, because in the mathematical sense, they do have inverses. It's just that we're reserving the word invertible for the case we're working with operators. Okay. The same idea applies though. If I have a map, what's that? Oh, is it? No, it is. Yeah, this is an isomorphism of vector space of an operator, a vector space of itself. I mean, it is. I mean, invertible maps are isomorphisms. That is, so Axler like he carves this out. So like a lot of authors are like would say this is an invertible map. They would characterize a bijection as an invertible map between vector spaces. But what he's trying to distinguish is he thinks about an isomorphism as a way of renaming one vector space into another one. And he thinks about an invertible map as a way of sort of resorting a vector space into itself. So that's just I don't know why he chose that way, but he's just trying to distinguish. It's an automorphism, right?
So just to clarify, T being an invertible map also means that T is an isomorphism?
Yes.
Okay.
Yeah, all the idea of isomorphism contains is the idea of bijection between vector spaces. Yep. No, you say it's an isomorphism. All right. So I know we spent a lot of time talking about this stuff today. I mean, we're hitting like we're sort of hopefully you guys got, this isn't too boring to go back to the big ideas here again. This is basically what the thrust of this exam is going to be. It's the ideas we talked about today, right? So this stuff, notice we also talked like sneaking around in there where the null space and the range too. It's sort of deeply like bound up with the idea of talking about eigenvalues and eigenvectors. So go back and read your definitions again. Go back and make sure that you like have an idea about how to approach those exercises that I told you to look at. And yeah, I'll see you tomorrow.
Okay, so I should confirm like so I know that T can have a low dimension value.
Yep.
And then for how many eigenvectors it can have, is that it can have